Hello guys and welcome back to class. Today we have exact ODE on the board. We are asked to solve this ODE. And first of all, before we solve this kind of question, we have to check if it is exact. Now, checking if it is exact, we need a necessary condition, and the necessary condition is given by this. You have your partial m by partial derivative of y has to be equal to the partial derivative of n by the partial derivative of x. So if I have something like this, if this one is equal to this from this place, then it is exact. If it is exact, I will just go ahead and integrate the both sides to get what my answer is. So with this now, how do I locate my m and my n? Now my m is always the one that has dx with it, and my n is always the one that has dy with it. Get these two things, they are different. I'm differentiating this one with respect to x, differentiating n with respect to x. I'm here, I'm differentiating m with respect to y. But I'm not picking my m as the one that has dy. I'm picking my m as the one that has dx. So from this place now, this is going to be my m because it is the one that has dx. You see, so this is my m and this is my n. So I'm going to do the partial derivative. This is going to be respect to y, and this is going to be respect to x. I'll compare the both of them. If they are the same, then it is exact. Then I'll just go ahead and solve from there. So integrating this, differentiating this with respect to y, I'm going to have 1 plus 2x exponential y. That's for this. If I differentiate this with respect to y, then if I'm differentiating this with respect to x, it's going to be easier if I just multiply the whole thing here by my x. So I'll have x plus x squared exponential y. So if I use this x and open the bracket, I'm having this. So differentiating this now with respect to y, or rather with respect to x, this is n. Look at the necessary condition. It says that I'll differentiate m with respect to y. It has to be the same when I differentiate n with respect to x. So I'm differentiating this with respect to x. Differentiate this, I'm going to have 1 plus, if I differentiate this, I'll have 2x exponential y. So if you check, these two results are equal. You have 1 plus 2x exponential y, 1 plus 2x exponential y. So in the simplest form, this is an exact ODE, is an exact ordinary differential equation. So since it is an exact ordinary differential equation, what I'm going to do is I will just integrate straight up from this point. Integrate. And let me tell you this, once I'm integrating this part of my n here, this is what I'm having for this part here. So my x, wherever I see my x, when I'm done with the integration, wherever I see my x, I'm going to impute 0 for x. So if I'm imputing 0 for x, check out this whole thing. Whatever the value of x is here by the end of the day, if I put it as 0, if it multiplies everything here will become 0. So this part will go out. It's just remaining this now. So I'm going to have the integral of y plus 2x exponential y dx is equal to the integral of 0. And you know, if I integrate 0, I'm going to have what? A constant. So I'll just put it here. I'm going to have this. So integrating this, thank God it's a constant here. Integrating this, I'm going to have xy plus 2x squared exponential y all over 2 equal to c. So I'll finally have my yx, or my xy, plus x squared exponential y is equal to c. So that's it. It's very simple, but the basic thing you need to do is to check first of all if it is exact. If it is exact, then the integration will be very, very simple. You check for the necessary condition and then you integrate like this. Do not forget this. Do not forget this. Do not forget this. When you are integrating, the right part that has your n your x is always 0. So all the terms that have x will turn to 0. If there is any term that is in y that doesn't have x with it, then that one can have a value. But if it's having x, then the whole thing there will turn to 0. So that's how it is done. In case you don't understand, you can ask a question in the comment section.